السلام عليكم ورحمة الله وبركاته. أهلا بكم مرة أخرى. Uh, we continue our lecture, which about polynomials over GF of 2. We talk about the polynomials generally, and we know how to make addition, multiplication, subtraction, and division using the polynomials. We use the polynomials to do those operations, and we are interested in the polynomials. There are two types of polynomials, the irreducible polynomial and the factor, the polynomials that they have a factor. So there are two types of polynomials. If there is a remainder, so this is some kind of polynomial, is reducible polynomial. And if the R of X is 0, so this is irreducible polynomial. Okay. So the irreducible polynomials or prime, I'm sorry, the opposite. So a reducible polynomial should have a remainder. But the reducible polynomial, they don't have a remainder, or the remainder is 0. We are mostly interested in the irreducible polynomials, or we call it prime polynomial. Okay, we will move to this after a while. We talk about GF of 2 first, then we move to GF of 2 to the power m. For example, we can do all the operations on GF of 2. They are very straightforward. We can use XOR to make addition and subtraction. So for example, 1 plus 1 equal 1 minus 1 equals 0. And 1 plus 0 equal 1 minus 0 equal 1, and 0 plus 1 equals 0 minus 1 equal 1. This is just XOR operation. If you look at the input, the output, if they are similar, they will give 0. If they are different, they will give 1. So addition over GF of 2 means XOR operation. Okay, and for example, I will show you now an example on how to make addition, multiplication, subtraction, and division over GF of 2. Take care, this is GF of 2. Okay, let me open back my camera to be able to show you how to do that manually. So this is my camera. Let's move to another example. Let's make the addition, multiplication, and division. It's straightforward, and don't worry about them. They are very straightforward. If just you make some examples, you will get used to them. So, for example, if we have the addition of x to the power 5 or x to the power 7 plus x to the power 5 plus x to the power 4 plus x to the power 3 plus x plus 1. And I want to add it to x3 plus x plus 1. This is just an addition. Okay, the addition, just plus here. The addition is just straightforward. I know that these are similar. I told you this is XOR. Similar means they are removed together. All similar things removed together. Okay, let me make sure the input is So the result is x to the power 7 plus x to the power 5 plus x to the power 4. Okay, let me remind you by the XOR again. XOR is important because we need it in our addition. XOR is 0, 0 equal 0, 0, 1 equal 1, 1, 0 equal 1, 1, 1 equals 0. So take care of this logic. So we have here 1 and 1. This is 1 and 1. So the result is 0. So this will be removed together. X and X will be removed together. 1 and 1 will be removed together. So the result is x to the power 7 plus x to the power 5 plus x to the power 4. Okay, what about multiplication? Multiplication is little long compared other to the other types of multiplication because the example here is long. Okay, let's take it step by step. X to the power 5 plus x to the power 7 plus x to the power 5, 4, 3, x plus 1. This is multiplied by 1 plus x to the power 3. This is multiplication. I do the same here. So I multiplied 1 by the entire polynomial. So this is going to give me x to the power 7 plus x to the power 5 plus x to the power 4 plus x to the power 3 plus x plus 1. And multiply x by all of them. So x multiplied by x to the power 7 is x to the power 8. And x to this one, x to the power 6. And this, x to the power 5. And here, x to the power 4. And here, x to the power 2. And here, x, only x. Of course, you can add plus here, or just no, because we don't need the addition here. We don't need the normal addition. It is not normal addition, it's XOR. The last thing is to multiply x cubed to all of the entire polynomial. So x to the power 3 multiplied by this is x to the power 10, and this x to the power 8, and this x to the power 7, and this x to the power 6, and this x to the power 4, and this x to the power 3. Okay, let's sum up. X to the power 10 it is alone, so it will be there. This is removed with that. x7 is removed with x7. x6 is removed with x6.
ليش دكتور انت بتجمع؟
This is XOR, not just normal summation like this is 1 plus 1 equals 0. Not plus, not or, it is XOR. Okay?
دكتور مو بشرط يكونوا تحت بعض عادي نشطب يعني.
No problem. I just not writing them the right way, but if you look at the slides, you will find them aligned very neatly.
Okay.
If you look at the slides, they ordered it, but for me, I'm multiplying very quickly, so they are not too ordered. But you know that x7, x6 is here, and x6 is here repeated, so you can remove them together. And for x5 here, we can remove x5 with x5. Yes. x4, we cannot remove it because it is repeated 3 times. We can say that x1, this one is removed by that one, but we have here x4. So I put x4 as a result. x3 is removed with x3, and the x is removed with x, and we still have x plus x to the power 2 plus 1. Okay, so the result is x to the power 10 plus x to the power 4 plus x to the power 2 plus 1. This is the result. Okay, let's move to the challenging one here. The longhand division. This is more challenging. So x to the power 7 plus x to the power 5, 4, 3 plus x plus 1. This is divided by x to the power 3 plus x plus 1. To get x to the power 7, I should multiply by x to the power 4. So I get here x to the power 7 plus x to the power 5 plus x to the power 4. I sum them with XOR, so this is removed with this. Sum or subtract, no problem. So this one is removed with that. That one is removed with that. You have x to the power 3 plus x plus 1. As you can see, plus 1. As you can see, we can have this exactly like that. So I just add 1 here. 1 multiplied by that will give us x3 plus x plus 1. This is no remainder. So if I divide these, this polynomial by that polynomial will give me x to the power 4 plus 1, the result of division. How to make sure of this? If you multiply these together, you will get the same here. Okay?
دكتور بس شو الفرق هو بين الجمع العادي يعني نفس الجواب بيعطي آخر شيء إكس أو؟
Huh? Again, can you ask again?
أنا قصدي أنتون في القسمة تحت
Yes.
بدل ما تطرح جمعت بيعطي نفس الجواب؟
Yes, in XOR it gives the same result.
بس هنيك أنت لما تجمع في السؤال اللي قبله لو جمعناه جمع عادي ما حيعطي نفس الجواب هذا.
Yes, but just because we are working GF of 2. GF of 2, we work in X, we do operations in XOR operation. Addition and subtraction, they have the same effect of XOR. So I added here, I added here or subtract, they have the same result. They are XOR. Okay? No problem?
What do you mean by GF?
GF of 2 is field. I defined the field in the first part of lecture. The field is just to follow some axioms and just have the multiplicative inverse. A field have operations on numbers, and these numbers have a multiplicative inverse. Okay, let me continue, and I will show you how we get the multiplicative inverse of any number in GF of 2. Okay. Okay, so now if you make multiplication, now if you make let's take an example for the polynomial. We can say that next slide, we can say that we can say polynomial. We seek the irreducible polynomial, irreducible. Polynomial. The irreducible polynomial. I'm seeking that irreducible polynomial to make the field. The field should have, for example, if I say A multiplied by B, the result should be in G, or F, if I define this as a field. So if I have A in F and B in F, A multiplied by B should be in F, and A added to B should be in F2. So this is the condition of the field. And also I have to make cycle, you know. So I use mod operations, but this time I will not use number like 7. I will use irreducible polynomial. Okay, I will use irreducible polynomial. Before I was using prime numbers. This is irreducible polynomial is the same as prime polynomial. So the same thing. I want to have mod operation done on irreducible polynomial to have this field in a cycle, like cycle, to cycle over the numbers. So if I do operations, will lead us to the same domain. I will not get out of the domain. For example, in integers, if I multiply 2 by 4, this will give us 8. 2 in integer, 4 is in integer, 8 is also an integer. This is for integer numbers. Just an example. We do the same here. We want to have A and B. If I do operations on them, will give us to another number that also in F. If A in F and B in F, the result of this operation should be in F. To do that, we have to make mod operation to cycle. If for example, if I multiply two numbers, will give us the same number, the same result will be in F2, even if it is greater than this limit, because you know that mod means that return back, make a cycle. Okay, so let me search for this irreducible polynomial. For example, I can say that f of x, okay, f of x equal x to the power 4 plus 1. This, in the previous example, let me check the previous example. In the previous example, I can say that x to the power 4. Let me check that example. Yeah, x to the power 4 plus 1 here divides the x to the power 7 plus x to the power 5 plus x to the power 4 plus x to the power 3 plus x plus 1. So this means this is irreducible. This is reducible. Reducible means that there is a polynomial that divides it. Here, we see that after we divide x by x cubed plus x plus 1, we have a result without remainder. A result without remainder means this is reducible. It has a factor. Like for example, 7 doesn't have a factor, but 8 has two factors. Has 2 and 4. These are the factors of 8. 7, no factors. Also, this has a factor. It's like 8. This polynomial like 8 exactly. Similar. 8 has two factors. This also has a factor here. And the other factor is the one here. The other factor is the one here. Here, this one. Just because if you multiply these two together will lead us to the long polynomial here. So this is reducible. Okay, let us see another type of. Okay, let's take another example. If I take x cubed plus x plus 1, I divide it by x plus 1. Okay, let's check this x cubed plus x plus 1. X cubed, to get x cubed here, I have to multiply by x4, x cube, x squared, okay? X squared by x is x cubed. X squared by 1 is x squared. Okay, remove this with that. And I have here x squared plus x plus 1. To get x squared here, I have to multiply by x. So this is plus x. X multiplied by x is x squared. X multiplied by 1 is x. So the remainder is 1. I have a remainder of 1. This means this polynomial is irreducible. Because it has a remainder here. It has a remainder. This means this one is not a factor of that one. It's like 7. The factor is 1 only. Only 1 is a factor, but others, there is no factor for 7. This one also, we cannot say this is the x plus 1 is a factor of, no, it is not a factor of that one, because there is a remainder. So we call this is irreducible polynomial. We can take this irreducible polynomial to be our mod the irreducible polynomial, to have this ring and to have this field and apply the remaining operation and make sure that we are in the same field when we make any operation. Okay, so this is why we need a reducible polynomial. Now we get that irreducible polynomial, which is x cubed plus x plus 1. This irreducible polynomial that we are going to use in GF of 2. Okay. Okay. And here, how to get a polynomial. Okay, let this aside now, leave it for a second, and we move to another thing, which is greatest common divisor of polynomial. Greatest common divisor of polynomials. We apply the same Euclidean algorithm. Euclidean algorithm. But here for polynomials. So let's take an example. What about the GCD of x to the power 6, 5, 4, 3, 2, 1, plus 1, and x cubed, x4 plus x squared plus x plus 1. Can you get the greatest common divisor of these two polynomials? Yes, we can apply the Euclidean algorithm. Just divide that by that. Divide, just longhand division. X is 6 plus x 5, 4, 3, 2, x plus 1 over x 4, x squared plus x plus 1. How to get that one? X squared. X squared by x4 is x6, and that is x4. Okay, let's put it here. And that is x3, and that is x1, x squared. Okay, I remove that with this, that with that, that with that, here with that. Here we get x5 plus x plus 1. I multiply by x here, so I have x4, x5, sorry, x5, x by x4 is x5 plus x to the power cube and x squared and x. So the remainder is here, x is removed with x and 5 with 5. So the remainder is x cubed plus x squared plus 1. So this is the remainder. I cannot move further, okay? So this is the remainder. I take this remainder and divide by, I divide that one by the remainder, as we do in the greatest common divisor between two numbers, like 3 and 5, or 13 and 15, something like that. I do it like that. 15 is, how many of 3 is 1 by 13? How many of 13 plus 2? So I get 13 here and say that it is, how many of 2? It is 2 multiplied by 6 plus 1. And I get 6. How many of 1? It's 6 by 1 plus 0. So greatest common divisor of 13 and 15 is equal to 1. But what about this one, this polynomial? I didn't answer this question yet. The greatest common divisor of this polynomial and that polynomial, I only do the division, that by that. The remainder is here. I take this remainder and multiply again. Make another multiplication as here. Sorry, division, not multiplication. Make another division. So x4 plus x squared plus x plus 1, I divide it by the remainder here, x cubed plus x squared plus 1. Okay, so how to get x4? So I multiply by x here. So x4, x3, and XOR, okay? Sorry. This is not true. This only, and we have x cubed here plus x squared plus 1. Sorry, this is not true. This remains because they are not similar. So x cubed plus x squared plus 1, we multiplied by 1 here. 1 multiplied by x cubed is x cubed. 1 multiplied by x squared is x squared. And 1 multiplied by 1 is 1. So the remainder is 0. This means the greatest common divisor of that long, okay, I'll write it back, x5, 6 plus x5. This is long story. So x4 plus x3 plus x squared plus x plus 1 and x4, x2, sorry, x2, x plus 1. The greatest common divisor of these two polynomials is the one here, which is x cubed equal x cubed plus x squared plus 1. This is the last remainder. Okay, you check this one. We divide that polynomial by that, and I get this remainder. And I divide that by that, and I get 0. So that the previous remainder, 0, and the previous remainder as GCD. The previous remainder is that one. So greatest common divisor of these two polynomials are that polynomial. This is a Euclidean algorithm to get the greatest common divisor of two polynomials. Okay, let me check with you the slides back. We get the slides back. Here, we share our slides to continue discussion. Okay, this is in GF of 2. In GF of 2, this is binary. GF of 2 means binary operations, okay? And we have seen how this is a irreducible polynomial, x cubed plus x plus 1. This is an irreducible polynomial. And we have seen how to get the greatest common divisor of these two long polynomials, and we get x cubed plus x squared plus 1. And now we move to GF of 2 to the power n. Now we understand how to make GF of 2. Now we move to GF of 2 to the power n. Okay, GF of 2 to the power n means we can have binary operations between the binary representation of polynomials. We can have a binary representation of polynomial. Okay, let's check this. This is addition for mod 8 arithmetic, but this addition is just, this is just XOR operation, okay? This is addition is just XOR operation. So let us take an example. Can we check this one? Okay, let me check another one. This one, okay? This is 0, 1, 1, and 1, 1, 0. We make XOR operations between them. So this is 1, this is 0, this is 1. Sorry for that 0. This is 0, this is 1. Okay. Now we have 1, 0, 1, which is 5 in binary. If you know about binary, this is equal to 5. Also, you can take anything. Anything is okay. You can see this is straightforward because if you make X operations between 1, 1, 1, and XOR operation between 1, 1, 1 and 1, 1, 1 is going to give us 0, 0, 0, which is 0 exactly. This is XOR operation. XOR operation. What about the multiplication? The multiplication is little needs some experiment. Here in the slide, he says that if we have integers 1, 2, 3, 4, 5, 6, 7, and we are working in 2 to the power 3, which 2 to the power 3 is 8. Mod 8 was not working because they don't have multiplicative inverse, but here to 2 to the power 3 we have a multiplicative inverse. And also he is just saying that if we have these numbers here, this is the number of occurrences in GF on Z8, means it is not regular. This is not regular occurrences. But in GF of 2 to the power 3, it is regular. If you count how many here, if you count how many 7s, how many 4s, how many 3s, how many 2s, how many 1s, here and there, you will find all of them 7. So this is just a characteristic for GF of 2 to the power 3. And returning back to the XOR operation, addition, and the multiplication. Okay, let's talk about the multiplication a little bit because it needs some understanding. Okay, let us take any question? Let's take this one. Okay, concentrate on this one and I will open the camera and show you how to make this one, how to make multiplication. After this example, you will understand the GF of 2, GF of 2 to the power 3, how they are working, okay? So I share my camera back. Okay, for GF of 2 to the power n, I take this example. I want to multiply 1, 1, 0 by 1, 1, 0, okay? 1, 1, 0 can be represented by polynomial. We can say there is no 1 because this is 1, this is x squared. So it is exactly as x squared plus x, okay? And this one is also x squared plus x because this is 1, this is x squared, and this is x cubed, and so on. So this is multiplied by x squared plus x. But here I want to make it a field. Why I want to make it a field? Because I want the multiplication not to go away. No, not to jump over this circle. I want the multiplication to remain in the same circle. So this is with mod, the irreducible polynomial that I told you about, which is x cubed plus x plus 1. Just this selection for the mod A, the GF of 2 to the power 3. Just they selected this because it makes the GF all the operations in the same field. The result will remain in the same field. Okay, I told you about, for example, I told you about the 2 multiplied by 4 is 8. 8, this is integer, and this is 4 is integer, and the answer is also integer. But if I want to make 2 by 7 mod 8, this also will remain in the same ring if I want to make a ring or cycle, because 2 by 7 is 14, mod 8 is 1 by 8 is about 6. So the remainder, the result is 6. 6 also in the field, which is defined by these numbers 0, 1, 2, 3, 4, 5, 6, and 7. So 6 here is the result. The result is in the field. Okay. So this is why I am telling you I have to use irreducible polynomial to be able to be able to make the result remain in the same cycle, not to get away, to jump over, or to get off the domain that we are in. We are in a circle. We don't want to get the numbers out of this. So I have to make the division by the irreducible polynomial. This one is selected. Okay, let us continue. So multiply that by that is like x squared plus x to the power 2. This is exactly x to the power 4 plus x squared plus 2x cubed. This is 2x cubed. Okay? But this is not true. Just because x to the power 4 is okay. X to the power 2 is okay. And remove that one. This is confusing. This is x to the power 4. And this is x to the power cube. And this is also to the power cube. And this is to the power 2. There's no 2 here. This is not true. But here is true. Just because I can get rid of that with that, because we have XOR operation. So the result is x to the power 4 plus x squared. This is the result of multiplication. How to make sure this is not getting out of our domain? Just divide this number, long division by, okay, let's take it another way. Long division x 4.
Doctor, why you remove x cube with x cube?
I remove x cube and x cube because we are doing XOR operation. The addition and the multiplication here, starting from, I don't know which number of slide, when I talk about GF of 2. Starting from this slide, all the operations after this slide is done by XOR. Okay, there is no addition, there is no real number addition or integer addition, it's just XOR addition. That's why I am confused here when I used 2x cubed. It is not 2x cubed, it is x cubed plus x cubed. X cubed plus x cubed is removed together because we are doing XOR. Okay? So x to the power 4 plus x to the power 2 divided by that irreducible polynomial, x cubed plus x plus 1. To get x4, we multiply by x. So x4 plus x squared plus 1. So I multiply, I make addition, and the remainder is 1. Okay? The remainder is 1. I think I have a mistake here. Yes, we have a mistake here. This is x. Okay, let's get back. X to the power 4 plus x to the power 2 divided by this one. We get, to get x4 here, we multiply by x. X multiplied by x cubed is x4. X multiplied by x is x squared. X multiplied by 1 is x. So the result is x. Okay? This is the result of division. What is x exactly? If I make operations, if I make it to convert it to binary, I say, okay, we have 1 x, x squared, x cubed, and so on. This is just x, so I put 1 here and 0 here and 0 here. What is the value of this in binary? This is 1, 2, 4. So this is 2. So the result is 2. Okay. Okay, so let me share back the basic. So here the result is 2. As you can see, now I know the result is 2. Okay. You understand? Now you understand why we use a reducible polynomial. Just to, as I told you at the beginning of the lecture, I want to make a cycle. Something is cycling, not to have operations that jump off the domain. I have to remain in the same domain. This is why we need the reducible polynomial. Okay, you understand this one? Or even you understand the operations? Any question?
Yes, doctor.
Okay. So anybody can tell me how to represent this in polynomial? This is in polynomial is what? Anybody knows? How to say this is a polynomial? Okay, nobody knows? Okay, anybody can tell me how to represent this binary number in polynomial? As I told you, this is just to write here 1 and here x and here x squared. So this is in polynomial, in polynomial it is just 1. Okay, so this is 1 in polynomial. Okay, let me check. What about this one? Anybody knows?
1x squared.
No, you have a good trial, but it is simple. This here is 1 and here is x.
1 on x.
Yeah,
Yes.
yes, 1 plus x. So this is in polynomial is 1 plus x. Oh, sorry, this big one. 1 plus x. Okay, okay. This one. Anybody knows how to make it in polynomial?
X squared plus x.
Exactly. Thank you. So this is x squared plus x. Sorry for that. Okay. Last one.
X squared plus x plus 1.
X squared plus x plus 1. Hagar, thank you, Hagar. Exactly.
You're
X
welcome.
squared plus x plus 1. So do you know how to, anybody knows how to make sure of this result? How to make it? Just tell me how. Not, I will not ask you to make it hand by hand. Just tell me the method. How to make sure this result of this result. We have here x plus 1 here, and this is that one. X squared plus x plus 1. And here, x only x. What I will do, multiply x by x squared plus x plus 1, multiplication. But this is multiplication in XOR, as I told you, in GF of 2. So it is XOR operation. Then divide the result by x cubed. This is the irreducible polynomial, x cubed plus, divide it by, sorry, x cubed plus x plus 1. So again, to make sure of this one is 5. Why it is 5? Just because I multiply x squared plus x plus 1 by x, and the result is divided by x cubed plus x plus 1. The result should be something like that. X squared plus 1. X squared plus 1, which is 5. Okay. Okay, let me just ask you questions to make sure these concepts that you handled these concepts. Okay. Okay, so Another question, why we say that x cube, why we say that, get ready for the question, x cube plus x plus 1 is irreducible. Why it is irreducible? Why we call it irreducible?
Because it has a remainder.
A remainder for what? Yeah, you are
And division.
in division by what? You are saying good words, but you just tweak it around. Just tweak it. You are saying the result, but this is not. It is just you are objecting the result. You are aiming to the result, but still. Which number? Which polynomial I should divide this one by the x cube plus x plus 1 by 8?
الدكتور الكومن ديفايدر.
Oh, greatest common divisor, but with what? This is just only one equation. Only one equation. Why it is irreducible? You know the factors of number factors. For example, 8, I told you about 8. It has 2 factors, which is 2 and 4. Okay, so the result, the answer for this question is because this equation has no factors. We cannot multiply 2 polynomials and the result will be x cubed plus x plus 1. There is no such thing. There is no 2 polynomials that multiply together and the result will be x cubed plus x plus 1. If you divide this polynomial by any other polynomial, we will have a remainder. As you have said before, I don't know, somebody of you shared that or said that we will have a remainder. So if I am dividing this by x plus 1, for example, if I divide it by x plus 1, we will get a remainder. This means it is irreducible. Okay, thank you for your sharing. I know that you understand the concept because it is just, you didn't study it, just listening to me, and I know that what you have obtained right now is okay. Okay, so let's continue. Now we have a multiplicative inverse for all the numbers in GF of 2 to the power 3. But there is a problem here. If you see 5 has a multiplicative inverse of 2. The multiplicative inverse is not straightforward. It is not straightforward, okay? We have to use this algorithm to get it. It's not easy. It's not easy like before. It's not easy to calculate the inverse of a number to be, for example, 5. The multiplicative inverse is 2. It's not straightforward. We have to use this algorithm. That one. Extended Euclidean algorithm. If we want to have an inverse for any number, we have to use extended Euclidean algorithm to have the inverse of the numbers in GF of 2 to the power 3, or any domain 2 to the power any, because in symmetric and asymmetric key creation we will use 2 to the power 8. So also we will use this algorithm. Okay, this is just, I want you to know the name of the algorithm. I don't want you to get into these details. Okay, I will even check it like that. There is no need to, I just want you to see it by your eyes. No, nothing else. I don't want you to study how these steps, it is a little difficult and it is outside of this course. Okay, I just want you to know that there is an algorithm. This algorithm is called extended Euclidean algorithm to calculate the inverse, the multiplicative inverse of a numbers in GF of 2 to the power n. That's it. Returning back to our table, I know that maybe we are not able to find the multiplicative inverse by hand or by easy way. We have to use that algorithm, but I can make sure that the result is 2. I can make sure this result is correct. How to do that? Okay, let me share my screen. I think maybe this is the last share. I share my camera back. So as I told you, we have here 5. The multiplicative inverse of 5 is 2. Why it is 2? Or it is 2, okay. Why it is 2? Just because I used Euclidean algorithm, extended Euclidean algorithm, extended Euclidean algorithm. Just to get that. Now I prove it. I prove that the multiplicative inverse of 5 is 2. Just follow me up, just one by one, just step by step. How to write 5 in polynomial? It is 1, 0, 1, which is x squared plus 1. How to write 2 in polynomial? Huh? Who knows? 2 in polynomial is how to write it? Anybody knows how to write 2 in polynomial?
0, 1, 0.
X only?
0, 1, 0 is how to write it in polynomial. X is what?
X, doctor.
Yes, exactly. Yes,
X only.
exactly. Yeah, X, only X. Now, I know that if I multiply X by X squared plus 1, mod that or reducible polynomial, it will give me 1. Remainder of 1, remainder. Sorry, no, not remainder. The result will be 1, okay? Okay, let me concentrate. If I want to think about anything that has inverse, for example, 6. The inverse of 6 is 6 to like that, and the result will be 1. Okay, so this is the result. Result should be 1. If I have a result of 1, this means this is true. This multiplication is true. I have to multiply this by that and get a result of 1, as we do here in normal numbers. Let's multiply it. So x multiplied by x squared plus 1 is x cubed plus x. Okay, long division by the irreducible polynomial, which is x cubed plus x plus 1, x cubed plus x, this one here. So I divide it by that. I take 1 and I multiply 1 by x cubed, which is x cubed plus x plus 1. Okay, so here we remove that with that, that with that, and the remainder is 1. This is the remainder. I don't care about the remainder. I care about what? The result. The result is 1. Okay, so I have a result here is 1. This means this is true. So the multiplicative inverse of 5 is 2. Okay. Okay, so now I think we finished our lecture today. Now I know how to prove any one of these. Okay, maybe in the assignment you will see something like 4. Why 4 is the 7 is the multiplicative inverse of 4. I want you to prove it, not to get the multiplicative inverse. Okay. this is exactly the same as this table. Exactly the same as this one, but written in polynomials. So that one here, it's the same, no change. Okay, and this is the extended Euclidean algorithm to find the multiplicative inverse. And I want you to concentrate on this slide. I just want you to make sure that you understand that if I want to make addition, so it is XOR. If I want to make multiplication, is shift plus XOR. If you remember the multiplication, it is like the result something like that and something like that and something like that, and then XOR them together. So it is shift, then XOR. Okay. Okay, that's it for today. And if you have any question, that's it for today. This is very long, very intensive, not long. It's very intensive lecture. It contains many concepts. You have to try it by hand. You go home, get out the papers and pencil and try to write down these operations and try some examples. And even I give you, I will raise some assignment today. It will you will be able to solve it if you get trained on these concepts. So we look at the lecture, I recorded it. You look at the lecture and follow up me, do the same thing, and then go to the assignment and you will find the same thing there. You will master the concepts. Any question? Anybody has a question? Anything is maybe not related to the lecture, anything.
دكتور بس عندي سؤال بسيط بالنسبة
تفضل.
الكويز الأول متى
ايوه،
حيكون؟ متى يعني حتحدد الموعد؟
الديدلاين الكويز الاول. الكويز الاول ديدلاين النهارده.
لا كويز يعني امتحان.
اوكي confused. اوكي الكويز ان شاء الله يعني انت سبقتني. الكويز ان شاء الله الاسبوع الجاي، ما هو متحدد في الشيت اللي معاكم. الكويز بعد شابتر 4. لو انت بصيت معرفش السيلبس وصل لكم ولا لا. في السيلبس موجود فيه.
دكتور كيف يعني؟
الاسبوع الجاي في كويز على شابتر 1 و2 و3 و4.
طب انا دكتور ما كنت عارف، انت هسه حكيت يعني انت ما كنت حاط على جوجل كلاس روم.
ايوه بس انتوا معاكم السيلبس ولا لا؟
دكتور انت لازم تبقى تحكي لنا انه مثل امتحان وهيك.
ايوه يا دكتور لانه كتير قوي 1 2 3 4.
يعني مش فاهم برضه. ما هو مكتوب اصلا مكتوب. طب انتوا عارفين ميعاد الميد تيرم عشان ما تجوش تقولوا له انت ما قلتش.
لا دكتور انت لازم تحكي لنا وتنزل على جوجل كلاس روم انه مثلا الاسبوع الجاي فيه كويز هيك. شو الاشياء اللي داخله؟
متى بالضبط بيكون؟
ايوه انا كنت ناوي اقول لكم دلوقتي بس انتوا سبقتوني. هو اسبوع مش كفايه للمذاكره؟
لا دكتور مش كفاية لأنه عندنا مواد تانية. إحنا منزلين 5 مواد كل سمستر فلازم قبل فترة.
طيب
تكون عارفين.
طيب بالنسبه اوكي ممكن الاسبوع اللي بعد اللي جاي. اوكي الاسبوع اللي بعد القادم خلاص.
اوكي دكتور.
الاسبوع اللي بعد القادم وكمان
او مثلا دكتور بالفترات.
Okay, I will give you a gift right now. Just 2, 3, 4. 2, 3, 4. I will not ask you about chapter 1 because it has very long theoretical things. I just want you to concentrate on the mathematics behind cryptography.
يعني دكتور ان شاء الله 2 chapter 2 3 and 4 not next week after.
Yes.
After 2 weeks.
Yeah, after 2 weeks we will take the first quiz in chapter 2, 3 and 4. Okay? كده كويس؟ يعني إن شاء الله الأسبوع اللي بعد القادم الامتحان هيكون في شابتر 2 و3 و4. الأسبوع بعد القادم. تمام كده؟ مبسوطين؟ اهم حاجه
دكتور
تكونوا
ركز.
مبسوطين.
لا مبسوطين.
مبسوطين مبسوطين.
طيب اهم
دكتور
حاجه
يعني نحن نركز على ماثماتكس بس؟
لا، ركزي على شابتر 3 2 و3 و4.
زين
أوكي؟
دكتور ما بتحدد شيء يعني معين؟
لا لا لا.
دكتور كل حد يحدد.
ايه؟
كلهم
دكتور
يحددون.
كل حد يحدد لنا المين بوينت على شو
إيه.
نركز يعني.
ما يعطونا
هو
الشابترات
يعني
كلها،
انا
كلهم يحددون.
ما هو انتوا بس يعني
ابدا.
اوكي. يعني انا لما اشيل شابتر واحد هو كده انا ما خففتش عليكم شويه؟ ما انا عارف ان الناس بتحدد.
لا
انا شلت
مثلا
شابتر واحد
دكتور
بدل ما اقعد
دكتور
اسيب لكم
مثلا
شابتر واحد ونقعد نحدد. فانا خففت عنكم شويه بس. ما هو التحديد ده تخفيف برضو. فانا شلت شابتر كامل فيه اكتر من 50 سلايد وكلهم نظري. فخليتكم بس للحاجات اللي
هي
المركزه. تمام.
دكتور هم يقصدون يعني شو المين بوينتس اللي يركزون عليهن حق الامتحان
والله
حق الكويز؟
يعني في كل شابتر شو
اكتر
مين
شيء
بوينت؟
في كل شابتر اكتر شيء ركزوا عليه الاساينمنت، الحاجات اللي بتيجي في الاساينمنت والحاجات اللي انا بكررها كتير في المحاضره. لكن اقول لكم سلايدات ايه مش هينفع صراحه، في الماده دي بالذات مش هينفع. اوكي
دكتور
تمام
على
كده.
الأقل يعني الثيوري بس حدد لنا الثيوري، ماثماتكس مو بلازم، الثيوري أكثر شيء.
ماله الثيوري؟
حدد لنا على الأقل من كل شابتر الثيوري بس.
ما فيش اصلا ثيوري فيه خالص، هو اصلا الشابترز كلها رياضيات. يعني مثلا شابتر 2 في تقسيمات الكريبتوغرافي، وبعد كده سيزر سايفر، وبعد كله حاجات رياضيات كلها. تمام. كلها حاجات حسابات، يعني ما اقصدش ماثماتكس.
يعني كل الامتحان بيكون حسابات.
لا اله الا الله. انا تعبت كده صراحه. يعني اكتب الامتحان واديه لكم وخلاص، ايه رايكم؟
دكتور احسن عشان ننجح كلنا.
بتاخذ اجر الله فينا والله.
انتوا اهم حاجه ذاكروا بس عشان تستفيدوا بالماده. ذاكروا وان شاء الله الامتحان يبقى خفيف، مش هصعب فيه ولا حاجه. خلاص
ان شاء الله. شيء لاب اليوم دكتور ولا ما شيء؟
ايه في لاب ان شاء الله.
عندنا لاب اليوم.
في لاب اليوم ان شاء الله. في حد ما تحضرش عايز يتحضر؟ في حد لسه جاي معانا في السيشن الجديد؟ خلاص تمام كده. خلاص اي سؤال تاني؟
يعطيك العافيه دكتور، ما قصرت.
الله يعافيكم، شكرا. اشوفكم على خير ان شاء الله.
مشكور دكتور.
الله يكرمكم جميعا يا رب، وربنا يوفقكم ان شاء الله. السلام عليكم.
السلام عليكم.